Hello, this is the second part of the chapter 4.2, and we'll talk about range and kernels of linear transformations. So let's just try to think a little bit how to define our vector spaces and vector subspaces. Last time we talked that the matrix is very convenient way to do it. We define the matrix and find the nulls and column space. But that's not the only way to describe it. Another way to describe our operation with subspaces and spaces is a linear transformation, which is just to remind you that the linear transformation from the vector space V to the another vector space W, it's just a rule which assigns one vector in V to another vector or image in the space W. And we only require such rule to have two simple properties. The first one is the image of the sum of two vectors should be equal to the sum of the images, and also that the image of vector multiplied by the constant should be equal to the product of the same constant C by the image of the vector. So it's actually not that demanding, just two simple properties, but it can define a lot of interesting properties. And we are actually need to define the null space using the transformation, because we discovered the null space has very important properties and it's actually useful in a lot of the applications. So basically all machine learning algorithms use the kernel. Without knowing the kernel of your transformation, you pretty much cannot do anything. So what is the null space or kernel of the transformation? Basically anything which has image equals 0. So anything which transforms into the 0 vector in our range W. And sometimes they're easy to define, sometimes it's not so much, and you will see several interesting examples and vectors, but I will kind of try to expand on this topic because, you know, kernel is not really a general linear transformation. It only has to be referred to the vectors. They can be applied to a lot of mathematical objects, and I will try to be here intentional, a little bit more abstract, and I'll ask you to find the kernel of the transformation which defined by the functions, not just vectors. For example, let's take a vector space which includes all real value functions which defined on the closed interval from A to B. And we don't ask too much from these functions. We just ask that they are differentiables in this closed interval from A to B. Then we will define a transformation D from our vector space V to the W, and this transformation will be basically change our function f, any function, to its derivatives, and that's why we'll require it to be differentiable. So pretty simple transformation. If you took multivariable calculus, you've probably done it hundreds of times. But let's just try to approach to the same problem from the linear algebra point of view. So let's try to find the kernel and the range of this transformation. And again, we have to think a little bit about this problem. So we have a vector space V, which involves a lot of functions, and they are transformed into the range W by the differentiation operation. So what would be our kernel? Again, anything which transformed into 0. And if you remember the calculus course, you probably remember that derivative of any constant is equal 0. So that's a pretty easy transformation. Any constant function defined on the closed interval AB will be a 0. So our kernel is a set of constant function on the interval AB. Okay, let's go into the range. So what do we need for the function to be transformed by a derivative? not that much. Our function has to be continuous, otherwise we cannot differentiate. So we can conclude that the range of our transformation is the set of all continuous functions in the interval a, b. Okay, and that's required nothing but a logic and a little bit of calculus, but there is a little bit more involved examples based on vectors. So I'd like you to go to the end of the chapter 4.2 and solve several practice examples.